Hey there! Let's take a few minutes together to quickly review the Work-Energy Theorem. To do that, come try a practice problem with me. I call this problem Air Gliding. Let's read it out. An air track glider of mass 0.100 kilograms is attached to the end of a horizontal air track by a spring with force constant 20.0 newtons per meter. Initially, the spring is unstretched and the glider is moving at 1.50 meters per second to the right. Find the maximum distance d that the glider moves to the right if A. The air track is turned on so that there is no friction, and B. If the air is turned off so that there is kinetic friction with coefficient 0.47. I encourage you to pause and try this for yourself, and I'll wait about 5 seconds before giving the answer. And time's up. So before we do any solving, let's just list our given. We have m equals 0.100 kilograms, k equals 20.0 newtons per meter, v naught equals 1.50 meters per second, and mu k equals 0.47. Now that we have those, let's solve this from first principles. We first try the case with no friction. We use the Work-Energy Theorem, where the total work done on an object W equals the change in its kinetic energy K. Recall that work is the amount of energy transferred by a force in moving a body through some displacement. Meanwhile, the kinetic energy is the energy associated with the body's motion. It is the amount of work needed to accelerate a particle from rest to some speed, and it is also the amount of work that the particle can do in the process of being brought to rest. In light of this, our motivating question to solve this problem becomes, what work is done by the spring on the glider to bring it to rest? Why? Because we know that the work done by a spring must be related to the distance it is stretched or compressed, and this work equals the corresponding change in kinetic energy of the glider, which is related to the glider's velocity. In short, this will help us relate d to v naught. Now, let's derive the work done by a spring. A spring has a restoring force proportional to the distance it is stretched or compressed from equilibrium, and the negative sign tells us that it opposes disturbances from equilibrium. This is why F equals negative kx. Now, the work done by any force along some path C is the path integral of F dot dl, where dl is the differential length along the path. We can think of this as summing up all the infinitesimal work done by this force in moving the object along this path. Since our motion is one-dimensional along the x-axis and our spring force acts only along this axis, the force and displacement are always aligned. We can therefore simplify this expression with dl equals dx and reduce the dot product to a normal product. The work on the spring is then given simply as ws equals the integral from 0 to d of negative kx dx. If we perform this integration, we get that ws is equal to negative 1/2 kd squared. Now that we have the work done by the spring on the glider, we can apply the Work-Energy Theorem. We get Ws is equal to K minus K naught, where K and K naught are the final and initial kinetic energies respectively. But what are these energies exactly? Recall that in general, our kinetic energy is given by K equals 1/2 mv squared. We can actually derive this by utilizing a kinematic equation and the definition of work. Since our final velocity is 0, we get that Ws is equal to 0 minus 1/2 mv naught squared. If we plug our expression for Ws into this equation and simplify, we end up with the even simpler equation Kd equals mv naught squared. Now, we can isolate d as follows, and substituting our given, we get that our answer is d equals 0.106 meters, assuming no friction. But what if we have friction? Well, we recall that since the glider is moving, we have kinetic friction, and this friction is proportional to the normal force, which yields Fk is equal to mu kn is equal to mu k mg, where it can be verified that n in this case equals mg. Note that friction always opposes the direction of motion, so that in our formula for work, the dot product of Fk and dl always has a factor of negative 1. This is why we get that the work done by friction Wfk equals negative Fkd is equal to negative mu k mgd. Now, both the spring and friction do work on the glider. We can now use these to write the work-energy theorem once again, summing up all the work to get Ws plus Wfk is equal to k minus k naught. We can substitute our expressions for work and use the same argument as before for the kinetic energies to get negative 1/2 kd squared minus mu k mgd is equal to negative 1/2 mv naught squared. We can actually clean this up a bit, multiplying everything by 2 and rearranging to get kd squared plus 2 mu k mgd minus mv naught squared is equal to 0. If we look at this carefully, we'll see that this is actually a quadratic equation indeed. So, we can apply the quadratic formula and get d equals negative 2 mu k mg plus minus square root of quantity 2 mu k mg squared plus 4k mv naught squared all over 2k. We can simplify this further by dividing out the 2's into the terms to get this, and we can actually do the same to the k. This gives us our final expression. D equals negative mu k mg over k plus minus square root of mu k mg over k quantity squared plus mv naught squared over k. Performing the calculations, we obtain d equals negative 0.132 meters and d equals 0.086 meters. But since we assume in our problem that d is positive, we ignore the first solution and get d equals 0.086 meters, assuming we have friction. This is now our final answer, and if we inspect it, we'll notice that the distance traveled before the glider stops with no friction is greater than the distance it travels with friction. This makes sense, since friction dissipates some of the energy that would have been used to move the glider. And we're done. Thank you so much, and I hope to see you next time.